So, Zach, I wanted to surprise you with a topic because I think it's a fun puzzle. It's not a physics puzzle and here's a problem, what's going to happen thing, but I just learned an interesting fact about iPhones that I didn't know. And it nicely dovetails into what we've been talking about with thermodynamics, in that I'm reading a book by Sean Carroll called From Eternity to Here, I think it's called, which is about the concept of time. And the iPhones thing is interesting in that it's about the way in which they keep time, which I didn't know. So the way it started was somebody posted a link to something that happened in 2018 where a hospital was getting an MRI machine installed. That day, the IT person received a whole bunch of calls from people saying their iPhones died, and he didn't know why. And so it was only iPhones, though, which was weird because he's like, well, first of all, it's probably like an electromagnetic pulse with the magnet or something. And so that's how it started. But since it was only iPhones, and I should say it's also iPads and Apple Watches. But no Android device was affected, no computers. He was super nervous because they have like a data center like around that MRI machine. Nothing, no problems there. No TVs, nothing. Only iPhones or Apple products. So he posted on sysadmin Reddit saying, what the heck is going on? Why are iPhones affected by the installation of an MRI machine, but no other computer things are?
Yeah, it's pretty weird.
If it's EMP, yeah. So it turns out iPhones, Apple products, use a different type of timekeeping device than other computers. And we'll talk about what I want to talk about today is timekeeping and how we do it with watches and clocks and stuff like that in computers. But the ones that Apple products use are so small that helium that was being used in the MRI machine's superconductor magnet, the helium gas was leaking into the hospital, not like in a dangerous amount, but just like it's supposed to vent, but the vent had a little leak and it was circulating helium throughout the hospital. That helium gas penetrated the timekeeping mechanism in iPhones and caused them to malfunction. Like that was the problem of it. And iPhones helium. Are the only ones that use it.
It's always helium. You always got to watch out for helium.
Yeah. I thought that was fascinating. So we'll talk about what the thing is in iPhones that keep time and why it's different and why it's interesting. But yeah, I thought that was fascinating. That it turns out helium gas leaking into electronic devices, literally just it's sealed in a little box, but the helium atoms are so small that they can penetrate through the silicon to cause problems.
So I have two things to say. One on helium is I'm not going to go into in-depth story, but there once was a group of scientists that claimed to potentially have found dark matter because they were seeing signals in their detector underground. And after a lot of review and trying to figure out what was actually happening, they realized it was seasonal, their detection. And I think what ended up being is when it gets, I think this is loose. So don't take all this as canon. But I think it was like when summer hit, the rocks, because these things are way underground, expanded a little bit and released helium into the chamber, and that got into their detectors and caused it to trigger to fault more often than not. So helium is it's known for this. And then the other thing that I wanted to say is I'm surprised because my expectation when you said iPhones keep time is, they just connect to a server somewhere and the server tells them this is what time it is. So the fact that they have a device on them that keeps time is pretty cool and interesting to me.
Maybe I shouldn't say keep time, and the number that you see on the clock on your iPhone is received through the internet, some timekeeping center.
The clock timing for the whole the chip that's running on
right.
Internet. Oh, okay,
exactly.
Gotcha.
That the clock, we know about computer clocks running in our computers. The device they use is sensitive. It's small enough and sensitive enough to helium getting inside it that it affects the clocks to the point where the iPhones just die. And the guy who was the IT person at the hospital, after people said it's probably helium, and they pointed to the Apple manual, the iPhone manual that says, do not use your phone around helium or other vapors that could get into it and cause problems. They specifically identify helium as a problem. And he put an iPhone in a plastic bag and blew a little bit of helium into that bag and sealed it. And when he did that, he started his stopwatch on his iPhone. And after about 5 minutes, the stopwatch starts speeding up a lot. 8 minutes in, or 8 minutes on the stopwatch is like 6 minutes in the actual recording of the iPhone. So yeah, it just like completely messes up the timekeeping. And then it eventually just freezes and dies and becomes unresponsive. You can't touch it. You can't do anything.
That's wild. That makes you like, this seems like it'd be so easy just to destroy like a crowd's a set of iPhones.
Yeah. And it wasn't like when people were joking like, oh, in the hospital were like all the nurses talking with really high pitched voices because of helium. And it wasn't noticeable. It wasn't that much helium. It was just enough that it could seep into the electronics and like cause problems. But yeah, it brought up another thing that I've been thinking about or haven't thought about in a long time, but I've noticed when I used to do research with superconductors, we had helium gas, liquid helium to cool off our superconductors to get them super low temperatures. That would sit in just a big tank of helium, liquid helium, and it would warm up and vent off the gas in the lab I was in. And I would sit next to it all day while doing research. And it was fine. It wasn't like a dangerous amount. We vented everything out. It was fine. But my phone GPS always had problems. Like I would always get the like, you need to recalibrate your sensor. And I would do the like figure eight. I don't know if you've done that on a smartphone. Yeah, I had to do that like every month. I didn't know why. And it was always a problem. And I thought my phone was like just a bum phone. I got a new phone, same problem. And I'm like, okay, something's up. And now I'm looking back, I'm like, I think the device they use for the gyroscope is the same thing that iPhones are using for their timekeeping clocks. It's like the same type of device called, I wrote it down, MEMS.
MEMS,
micro electromechanical system. So the phones use gyroscopes that are MEMS, just super small electronic, like physical things made out of silicon that are mechanical. So the gyroscope is like measuring orientation of its little silicon thing. Same thing with the way iPhones keep time now is using MEMS for their clocks instead of what most computers use, which is a quartz crystal. We'll talk about the whole episode. I want to talk about like how those devices work, but I thought the story of the person in the hospital was a good lead into it. And yeah, it made me question, did helium mess up my phones when I was doing research?
Yeah, it sounds like probably.
Yeah. And the fact that it was across multiple phones while I worked there was like, man, I had no idea I was getting my phone ruined sitting next to helium. Which were Android, there were Android phones back then, not iPhones. But yeah, cool. Timekeeping. I wanted to talk about that topic in the sense of the Sean Carroll book, where he starts off talking about the concept of time as either the moment when something happens or the length of time between two events happening, and how those two concepts have to be completely separate from each other to get a more accurate depiction of the concept of time, is that we separate those two things. Like normally you would think about like where something is by saying it is here or it's in relation to something else at some like measurable distance away. We're comfortable with that as like the concept of location. And I don't know that we would necessarily think of time in the same way, but he's bringing up points where it's very important in relativity in particular to think about those things as different things. The time length between events and the moment when something happens are not the same thing. And he goes into his whole book is about why that is, or a lot of the book is about why that is. So what I wanted to talk about today was the keeping of time, the measuring the amount of time between certain events using computers. And we can go back to before computers with clocks and the way clocks keep time. All of this, any way to keep time, we need something that happens regularly and in a fixed known interval, like some standard of time. So we used to use grandfather clocks with the pendulum, and that would just go like tick tock. And we would adjust the little weight on the end of it to say, okay, it's this many oscillations per second. Hopefully one is the point to get one tick and a tock per second. But there was a problem with using pendulum clocks to keep time specifically on ships. And they tried to keep time like when you're on a boat that's rocking in the ocean. But if you used a pendulum clock, it's completely messed up because the entire boat is rocking back and forth itself.
Yeah, it'd be like shaking your grandfather clock.
Yeah. Or a grandfather clock like during an earthquake or something.
Exactly.
It's going to be messed up. But yeah, put it on a boat. It's totally not going to work. You can't keep time with a pendulum clock. So it was like a technical problem to keep time while at sea. And do you know the fix, how they came up with the fix for that?
I don't know that one.
It's the standard. What we use now is on watches, pocket watches, and things that are wound up is to put a mass on a spring. And it's not just oscillate back and forth, because that could also have problems with being out in the water, but like a rotating spring, like a twist that swing, like spins back and forth. So there's like a massive wheel that rotates when the spring gets sprung. And then you have to sit there and wind it back up so it has more energy and can keeping time through its oscillations. So from pendulums into springs, and that's the inner workings of a wristwatch, is like a little wound up spring inside. But we've moved on to electronics, and we need another standard. So we have masses on springs. One of the things that we can do is ring a bell and just listen to it at the frequency that it's ringing and use that as the standard. You could put a little piece of metal in there and hit it like ting, ting, just like electronically, have a little mechanical hammer that jiggles and just rings the bell. That totally works, but they've gotten better at using smaller things that are putting out their own electrical signal. So part of the problem is powering the little oscillations that happen lots and lots of times per second. And to keep it going, like we have to mechanically wind up our watch, we need to electrically charge our little circuit to run the clock. Right. What they use is a crystal of quartz. I'm sure most people have heard of like quartz watches. It's quite literally a little piece of rock inside a watch or inside a circuit inside your computer. And it just wiggles back and forth at a particular frequency. But the cool thing about quartz is it's piezoelectric, meaning if you squeeze it, it outputs a little bit of electricity. Or counteract, like the opposite of that. If you run electricity through it, it'll squeeze itself. Yeah. So it like deforms. So they use the quartz crystal to build in kind of a feedback loop. And it's a nice timekeeping feedback loop where every oscillation outputs a little bit of a voltage. And then that voltage gets amplified and fed back into the crystal to keep it driving. So it's like powering itself each cycle, squeezing. You do need a battery to amplify the signal, but the cycles per second, it never decays. If you just flicked a tuning fork, it would ring, but it would decay away over time. So they're using a battery to keep that from happening to the quartz. So I think it's pretty neat. They figure out exactly the standard for the number of cycles per second. Because imagine the pendulum, like you adjust the amount of time per tick by adjusting the mass, like where the mass is hanging on the end of the pendulum in the grandfather clock. You can do something similar with a tuning fork. Like you get tuning forks in different frequencies by adjusting the mass of the fork, like how much material is oscillating back and forth. Same thing with the quartz. The way they manufacture it, the quartz crystal, is to cut out a quite literal tuning fork worth of quartz. It looks like two prongs. And then I think they add metal to it, like gold or something like that, to get it more massive than it should be. And they keep adjusting it and measure how quickly that tuning fork of quartz oscillates by shaving off more and more gold until it gets to the exact frequency they want. And so the frequency they want is, I wrote down the number, 32,768 hertz. So 32,768 oscillations per second is like what the standard is for quartz clocks in computers and quartz watches and all that stuff. Do you know what is nice about 32,768?
32,768. No mathematical, numerological interesting things come to mind.
It's a nice power of 2.
Okay.
So that's the big benefit to it. The other thing is we want something like if you used a real, quite literal tuning fork at 440 hertz in your watch, you would listen to it next to your ear and it would just hum. And it would be this audible noise that's pretty annoying to just have on your wrist at all times. Yeah. So they picked a frequency that's outside of human hearing, which caps out about 20 kilohertz. So they need something higher than that. And it's nice to be a power of 2 for use in computers and digital watches, just for the circuitry to make it easy to count how many oscillations it's happened. So you don't want a non-power of 2 for that. So the 32,768 is the first power of 2 above human hearing. So it's 2 to the 15. So when the little quartz crystal squeezes the prongs of the tuning fork, quote unquote, it sends a little voltage. and then it relaxes and the voltage drops, and then it oscillates squeezing again and the voltage goes up. So every time the voltage goes up or down, one of the little circuit counters flips. The ones digit that flips, and then you get the next digit up will flip every other cycle. And then every fourth cycle, the next digit flips. So you're just like have this counting circuit, literally just flipping switches.
Right.
And on the 15th one, or I think actually on the 14th one, since it's 2 to the 15, when that one flips, it's taken 1 second because the crystal itself has oscillated 32,768 times. And then the final like 2 to the 15th counting switch flips, then that tells the watch, okay, it is now 1 second later. And you just pay attention to that one. That's the one that tells you when seconds change.
Cool. Yeah, that makes sense.
Yeah.
So you're just literally counting in binary all the way up to to the 15, right? So 32,000.
Yeah, exactly.
But
you literally
only
just
have to
counting
watch the last one. Yeah.
Right. So it's important to manufacture those little quartz crystals to be exactly that frequency, which depends on the mass. So they, again, take a little bit of crystal rock quartz, etch it away, shave it down to being like a shape of a fork, and add a little bit of stuff to get it close. And then they keep watching it by shaving off more and more of that extra stuff until it gets to exactly the frequency they want. And that's your quartz crystal. And it lives in a little in-housed box on your computer and your watch. You can take them apart and they literally look like tuning forks the size of a grain of rice.
With so wires. Is this something you can see with your eye or?
Yeah. These you can see with your eye. You can hold it. And like I said, it's about the size of a grain of rice. And they're usually attached up to the counting circuit and some other stuff. But yeah, that's it. That's the timekeeping mechanism. It gets a little bit of power to amplify the oscillation signal and to keep the crystal moving. But yeah, that's how most computers and smartphones keep time until iPhones started using something else.
Wait, but that's slightly different though, right? Than like how like your Intel i7 CPU keeps time in terms of managing its clock cycles, because those work at 4 gigahertz or something. Is that true? Or
I don't know. I would imagine you need a faster clock. Yeah, you're right. If it's a 4 gigahertz processor, do you need a quartz crystal that can operate at that high number of hertz? Because you'd need to know like when a bit flips in your counting. Because the resolution of something that's 2 to the 15 can only come down to 1/32,000th of a second. But if you're doing some flops in the 4 gigahertz range, it must. Or maybe there's some fancy way. I don't know the answer to that question, but maybe there's a fancy way to wire it up that you don't need a crystal going that fast as your processor.
But I think if you were trying to keep human levels of time, crystal quartz is plenty fine. You have 32,000 bit, or I guess 15-bit resolution. So, but 32,000 points you can divide your second into. That's way more than a human needs.
Yeah. I'm quickly looking up. It looks like you don't need the crystal to do the timekeeping at that high frequency.
Yeah, I'm looking at, there's a common type of timer that's used, especially in like introductory physics. I think it's probably still used in some digital circuits, but it's a little slow, I think, for modern times. But it's called a 555 timer. I think they typically operate around like 1,000 hertz or something. Nothing too crazy, but it's literally just some digital gates basically hooked up in a specific way to make a clock, pretty much, that just flips back and forth 1,000 times a second. No crystals, just transistors.
Yeah, I'm wondering if you could wire up a timekeeping device in a computer that's offset by like a fraction of a second in a way that like 2 crystals that are 32 kilohertz can be offset by a little tiny amount so that it doubles the essential resolution of the clock. I don't know if that's how that works or if it's possible.
I'd imagine you could also maybe just do like there's probably some weird mixing type of things that you can do to like double your frequency or that sort of. There's a whole lot of crazy circuits out there that do a lot of signal processing. And so I don't even pretend to start to know the smallest amount of those. Yeah, I don't really know how like that works. But so I guess the types of timing, though, that we're talking about here is human stuff your stopwatch would use, human trackable amounts of time.
Right. Right.
Not like what your processor is doing necessarily.
No. Right. Yeah. So this is for like actual timekeeping clocks that your stopwatch on your phone or on an old digital clock or digital watch could maybe go down to a microsecond. No, probably not microsecond, probably like millisecond.
Although I don't know any of this, so I'm just like trying to connect things together. It seems though that somehow that human time scale clock, the quartz oscillator in the iPhone, is critical to the entire functioning of the iPhone. Otherwise, it's not like it just breaks your stopwatch. It sounds like it breaks your whole phone. So, somehow it's more critical than I'm giving it credit for. But okay, all right, yeah. I was just curious. I didn't know how because by human scales, 32,000 times a second is fast. By your computer scales, it's super slow.
Yeah. So to improve the quartz crystal requirement and basically get a smaller and smaller timekeeping device in your phones, Apple started using their MEMS, little micro electromechanical systems that are silicon etched to be a certain shape of a tuning fork, essentially. So instead of a grain of rice sized piece of crystal that's been like adjusted to be 32,000 cycles per second, they use silicon tuning forks that are like precisely created and manufactured, and they're extremely small. And yeah, they live inside of another sealed box. But that little box is apparently permeable to helium and maybe hydrogen, and small atoms can get inside there and cause problems. So yeah, the way that they manufacture those things is fascinating, because it's essentially you're creating a mechanical tuning fork created out of the silicon wafer, which is also holding the mechanical tuning fork. It's all like the fact that they get that precision at such a small scale is ridiculous. Like the way we can control it. Like the first came out in like the 80s, the idea of being able to do this. And then our manufacturing has gotten better and better to where we're now able to actually build them and use them.
Yeah, I think we typically use electron lithography at this point to get that small of things, where lithography is the process of essentially just taking some sort of material and you put it on top of the silicon, and then you put a mask over it that is either, so it blocks out light or lets light through, or electrons in some cases. Mm-hmm. And when the electrons come through and when they hit the material on top of the silicon, it alters it chemically and somehow. So then when you take that whole wafer and then you put it into a bath of some other chemical, it washes away parts where the electrons hit and leaves parts where the electrons didn't hit, or vice versa. And then you can put that whole thing. So now you have a pattern of silicon exposed to the air, and then you can put that in like some other bath that'll eat away the silicon or something. So yeah, it all depends on like what is your diffraction limit, basically.
Yeah, we're getting the limits of physics.
Yeah.
Yeah. I forgot. This is exactly what you used to do at Keysight, right?
Yeah. I worked with these sorts of things. Yeah.
Yeah. So yeah, you're pro at lithography. But yeah, that is exactly what they're doing, is manufacturing and etching away little silicon to get mechanical tuning forks that oscillate at a certain frequency. And they apply a little bit of charge to them that causes the oscillation to start and continue just by repelling charges and stuff. And they detect how quickly the little arms of the tuning fork oscillate, and change the stuff that the thing is oscillating in, and it adjusts the oscillations of the tuning fork enough that it throws the entire computing system out of whack, and it doesn't work. Like literally just freezes. And it's the instructions say, if it's exposed to helium, like helium got into the little silicon tuning fork area, just turn it off, let the battery totally discharge, and wait a week, and the helium will come back out naturally. But yeah, you just have to wait. So
yeah, so it must get in, and then it's probably fine. It's got to be fine for your watch. Otherwise, we'd know about this. Like people would know, oh, don't bring my watch near helium. We would have heard about this, I think. So like, I'm guessing it's because these things are so dang small that a helium atom is enough to throw off the frequency of it. Like you're putting a little gas in there.
Yeah, I think it's like adjusting the properties of the gas that's inside the sealed box enough that the tuning fork arm oscillates at a different frequency than expected. Yeah.
Yeah, that's wild. That's so cool.
Yeah. Yeah. I would imagine it probably affects quartz as well, but something the size of a grain of rice.
Right. Yeah.
If you swap out a few nitrogen atoms with helium atoms, it's not going to cause a big difference. Or if you increase the pressure a little bit because helium got added to that sealed box, it's not going to affect a grain of rice size thing that much. But an etched little tiny piece of silicon definitely would be affected. So yeah, I thought that was really interesting.
That's super cool.
And it ends up that somebody had an iPhone 5 and it was not affected, but iPhone 6s and above were affected. And that's when they swapped from quartz. Yeah. Yeah, exactly. But yeah, I would imagine it did affect other things. Like I was saying, like anything that's using MEMS, just anything that's mechanically functioning on a really small scale of MEMS, which are like micron sized, millionth of a meter, that could probably be affected by helium getting in. So yeah, gyroscope sensors on phones, which are MEMS or have been for longer than the clock timekeeping mechanism, I think it would be affected. And I'm willing to bet my problems with GPS on my phones back in the superconductor research days with helium floating around me caused problems on my phone, and I didn't know it.
Yeah, I 100% believe that. I want to ask around right now because that's the physics building at UCSB, because there are quite a few people that use liquid helium, and just see if they have any issues.
Yeah. Yeah. And if they use iPhones, and yeah, if they've noticed any problems. So super interesting. You can read an iFixit article talking about it. And if you search iPhones are allergic to helium in 2018, somebody wrote up an article on iFixit talking about it. And then there is a super cool YouTube video of somebody reproducing it and setting up like electrical sensors, measuring what happens to the little MEMS system as you add helium to it. And then what they did is they actually took it apart and like not etched, but sanded down the little chip thing and looked at it under an electron microscope. And you can like see the forks of the tuning fork thing. And yeah, he just did a teardown, but like a microscopic teardown, like getting into the electron microscope imagery of what the MEMS thing looks like inside an iPhone. And those little things aren't that expensive. Part of the reason why Apple switched to them is they're cheaper, but they also take less power to keep the little tuning fork running. And they're probably the biggest reason is they're a hell of a lot smaller. So you can get them into much smaller devices.
Yeah.
Which is important for the little Apple Watch. You don't want a grain of rice inside your Apple Watch is a significant portion of the volume inside there. Well, cool. That was just a quick, fast, fun topic.
I have either potential questions and or potential small things to add, or we could talk about maybe going in detail for next week or something. I'm not 100%. But my one question is, though, to go back to where you started with the Sean Carroll book. You said that there's the difference is when something happened, or like the difference between two things happening. And I think I'm guessing that the silicon oscillator or the quartz or whatever, that's the difference between two things happening. Is that right? That's because it's a period of some sort that you're measuring versus the exact moment something turned on or something like that.
Yeah. I think what Sean Carroll is getting at is the issue of simultaneity needing to be thrown out of our understanding of physics with relativity. And so in that, I would think if we take a movie of something happening, the frames are moments in time. And we say, okay, in this frame, it's showing this is happening. That happened at that moment. And then there were so many frames until something else happened. But then somebody else recording the video might see the frame when the thing happened, and then a different number of frames until it happened again.
Right.
And so the person would say, okay, these things happened this far apart, but you would say these things happened this far apart in time. And they wouldn't agree. And so even though the same thing is happening, the simultaneity of somebody watching those things is not absolute.
Gotcha.
And so we can think about that in terms of the cycles of a quartz crystal, counting an amount of time between things. Yeah. Being not an absolute fact of physics.
The other thought I had, things maybe to add to this for now or future, is so like at NIST, which is what does NIST stand for? The National
Institute of Standards and Technology.
Yeah. Yep. That's it. Yeah. They're not the only ones, but they're probably most well known for this. Their job is to basically define every constant that we know as well as as humanly possible. And so they try all the time to define the second better, or to have a better way of measuring it. And I think one of the best ways that they were recently doing it was with cesium atoms. But didn't we just redefine the second in 2019, I think?
Yeah, I'm looking it up right now. Yeah, we had a change of what is the fundamental units, the base units. So 2019 redefinition of SI units. The old one, it looks like the second we still kept, and it's defined the same way as a difference in oscillations of a cesium atom.
Okay.
That one didn't change.
Yeah. Okay. So yeah, that
might not be true. Sorry, I'm just quickly scanning the page. But yeah,
I think that sounds right. And that's some sort of optical clock system, some sort of AMO system that they have to keep time. But then that's not necessarily the only way. One interesting thing I just recently saw in a Quanta article is that there's this problem that was discovered probably in the 20s, but no one wrote about it until I think the 50s. I think it took an engineer. I feel like it always takes an engineer who just doesn't know any better. He's not in the physics culture, but they measured how long it takes for a particle to tunnel through a barrier, quantum tunnel. And when you theoretically calculate it, it tunnels through the width of the barrier faster than the speed of light. Then it would take a photon to travel that distance. And
okay,
everyone thought, okay, this isn't real. We're not going to publish this. We're not going to talk about it until this engineer did it and was like, what's going on here? Have you guys seen this? And so I think that it's maybe named after him, or he's credited with it. But so people have been pursuing how to do this to actually try and measure it, because this is just theory that's predicting this. And I think in Toronto, they have actually done it by shooting, I think it maybe was cesium, I'm not sure some atom through a barrier. And what they do though, is they use Larmor precession to measure time. So Larmor precession is when you put a atom with spin, I think, in a magnetic field, the spin will precess around the magnetic field, and you can
like a top.
Yeah, and you can time how long that takes. So that's another kind of way of keeping time. And so what they did is they shot these atoms through a barrier, and while it was in the barrier, there was a magnetic field present. So it started precessing once it entered the barrier that was tunneling through. And so you could time how long it took to go through it by how far it had traveled in its precession before it exited. And apparently their calculations show that it traveled faster than the speed of light through the tunneling barrier. I think in the Quanta article I heard, they talk about that it seems to be fine for now because there's no way it travels. It seems, okay, if you just take for face value that everything they did is right, which we don't 100% know, and it travels faster than the speed of light, then the only way it would cause a problem is if it leads to some sort of causality paradox or something like that. Or you can transmit information faster than the speed of light, which would lead to a violation of causality. And it appears as though that there's not a good way to do that with this method yet, I'll say. So.
It seems, the problems are usually resolved by saying when people bring up faster than light stuff occurring, the usual answer is, so you're not transmitting information, so it's fine, basically. And maybe that's what this is. There's no information being transmitted. And it usually gets resolved also by taking into account quantum entanglement. So maybe that's like an entangled state of, is the particle on one side of the barrier or the other, and it's entangled, so it's faster than light, quote unquote, but it's really just collapsing down from one state into another. I don't know.
Yeah, there's a whole bunch of weird things with this technique, because like a particle traveling tends to be like the wave function is a Gaussian pulse. So there's some chance that the particle is way ahead of the mean, and there's some chance that it's way behind the mean. So there's ways to look at it where it's like, oh, if it was in the leading part of the Gaussian that entered, and then we measured like the exiting part or something, then maybe the time wouldn't. But if you do it a bunch of times, you make your measurement lots of times, then you still see the effect. It's not just this random rare instance of it. But I think it's just that's it. Yeah, it's a new thing, but I think it's literally you can transmit a particle faster than the speed of light through a potential barrier. It's just like, it's not likely to happen. And if you were to do it over a useful distance, like any human scale distance, you get an exponential decrease for the odds of a particle being transmitted through a barrier with the thickness of the barrier. So I think these are like laser light barriers. So it's probably very thin, but it's not like it's like traveling from one room to another even faster than the speed of light. It's like nanometers, probably very small distances. So there's really no way that you'd be able to use that and the time that we're talking about, like faster than the speed of light, is, I think it's on the order of peak. I should have the article in front of me. I'm just loosely quoting, but the way the main point of that, outside of the interesting quantum phenomena, is another way to keep time is through kind of this alarmer precession, because that was one of the big problems with this whole experiment, is how do you best keep time for this? Because there were some people who tried this beforehand and they were unable to, like, their methods of keeping time were pointed to as flaws for the experiment. And so they were saying, okay, theorists were saying, okay, you didn't actually do this because I think that this is flawed, but people are on board with this alarmer precession timekeeping.
Got it. So if you're doing an experiment to measure the length of time something happens in, just throw out the Larmor precession and everyone will be like, okay, good. I guess you're right.
Yeah. I don't know enough details about it to know why that is the preferred timekeeping mechanism.
Yeah. You're like, no, I did the Larmor precession. So everything's totally fine.
Yeah. I'd have to reread the article and go into it a little more deeply. But that's what I was saying. If we wanted to add to another part of this, that'd be one. We could talk about how we keep time with these advanced tools.
I'm looking at the definition of the second, which changed in 2019, and the Wikipedia article on the 2019 redefinition of the SI base units. It says the previous definition was the second is the duration of 9 trillion. Is that right? Yeah. 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels, look at that in her name, of the ground state of the cesium-133 atom. The previous definition was a whole bunch of periods of radiation of light coming from the transition between hyperfine levels in a cesium atom. So some electron changes from one level to another and it emits light, and we can look at that light and count how many periods of radiation did we get from that light. That defines the second, when there are 9 trillion blah, 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 blah periods. So that's the old one. The new one says the second is defined by taking the fixed numerical value of the cesium frequency, and it redefines what that is, the unperturbed ground state hyperfine transition frequency of the cesium-133 atom. So it says take the fixed numerical value of that to be 9 trillion blah, 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 when expressed in the unit hertz. So it like defines the hertz in terms of, it backwards defines the number of periods from that cesium frequency and says, whatever you measure there, that number is this. So don't count it. It is this, like we promise. That's what that number is.
Yeah.
And so if you say, okay, look at the light here and it count as this many frequency oscillations, then you say, okay, that second then is defined to be that number divided by the light that you just measured, which is equal to 1 second. So it's the same, but a little bit backwards.
Yeah, because before, what was the
the duration of a certain number of periods.
Okay, and now they're saying 1 over that duration is a set fixed thing. Is that right?
It's saying, yeah, basically. That's basically what it is. I like their example too of changing from unit type definitions, changing from those to constant type definitions, which is what we do now. So unit type definitions is there is an example of the thing, and that's how you define your unit. Like there's a stick that is in France that is defined to be 1 meter long, and everything is 1 meter if it's the same length of that stick. That's the unit example type. The old definition of an inch, it was defined in 1324 to be the length of 3 barleycorns. That's what an inch is.
Like of three.
So find barleycorns, count out 3 of them. That's your inch.
Wow. I feel like there's got to be a distribution.
We laugh, but we used to have the kilogram. I said the stick example for the meter that we changed a while ago, but up until very recently, our kilogram was a literal block of metal in France. That was the kilogram.
Yeah, up until 2019, I think, right?
Exactly.
We switched to this watt balance system.
So the new system, instead of looking at things in nature and counting in them and saying this is what it is, they take physical constants like Planck's constant and put a fixed number on it and said it is this. There's no more uncertainty in Planck's constant. It is 6.626070015 times 10 to the minus 34. There's no uncertainty after the 7015 part.
Yeah, then that's constant. And however that propagates into changing other things, those things now carry the uncertainty.
Exactly. Yep. And the kilogram, it's defined to be a fixed number, which represents the speed of light squared, divided by, I see what they do. Oh, they're tricky. So the way they define 1 kilogram is they take all the constants that make it up, like Planck's constant, the frequency of the cesium transition, and the speed of light, and they take those numbers. So it'd be like defining the number 1 by saying it is 2 times 1/2. Like that's kind of what they're doing. Like they're saying, we know what 2 is. 2 is well defined, but we didn't define 1. 1 is defined to be 2 times 1/2. That's what 1 is. Yeah. That's like basically what they're doing. So the kilogram is defined to be Planck's constant times the cesium frequency divided by the speed of light squared. But that's not equal to 1. So you have to multiply that by 1 over Planck's constant, like the numerical value for Planck's constant, the numerical value for the cesium transition divided by the numerical value for the speed of light squared. That's how they define all those things. Very backwards, sounds like, but yeah, start with your physical constants and then rearrange them to get units of mass.
Yeah. Define all the things that we think that don't change in the universe, and we'll make those the basis for measuring.
We changed our whole inch system by saying 1 inch is defined to be 2.54 centimeters. It is that fixed number. Mm-hmm. So the inch is defined now in terms of meters, or it has been for a while. But before that, it used to be 2.54 and some other numbers, but they just changed it. They're like, no, I'm tired of having some uncertainty in my inches. Just tell me it's 2.54.
Yeah. And we should just get rid of the inch in the first place.
Yeah.
Let's just
agreed.
Let's have the 1 unit system. It's so much nicer.
Yeah. Cool. So yeah, that's the definition of the second as of 2 years ago. May of 2019. It was the 144th anniversary of the meter convention.
I'd like to imagine that's just a bunch of people. There's two sides of an aisle. One group is saying, no, we need to add length to the meter. And the other group saying, no, we need to subtract length from the meter. They're just going back and forth.
It's like progressive meterists and conservative meterists.
Yeah, exactly.
I think it's meter, not in the length of the meter, but like the word meter being like measurement, Latin. Yeah.
I like that less.
That's not as interesting. Could you imagine if units were like voted on? We were like democratic with our decision about units and like it changed every 4 years. We're like, oh, the second's up for a referendum this year. We got to vote on its new definition.
Oh God, could you imagine all the crazy units Trump would have came up with? There would have been like, all the units would have been like, this is a Donald, this is a Ivanka, this is a...
Yeah, they're just all Trump. A Trump second, a Trump meter, a Trump kilogram.
Yeah, exactly. He's defined to be one Trump of mass or whatever. So like everything is based off of relative to Trump. We'd all be really light then, though. That'd be nice.
Yeah, fractions of Trumps.
Yeah.
Wasn't the foot defined to be the king's foot size? That's the king. I don't know what king, but at the time, like the foot is measure the king's foot. That's what 1 foot is.
I know about the cubit, which was like the forearm length. And that was, I think, relative to whoever was in charge at the time. I don't know about the foot, how that came about. I know that the meter, I outside of just having an official meter somewhere in France, there was, and there still is, I think it's in Trafalgar Square, a cutaway system thing there that has basically 2 bars on it. And the distance between those 2 bars is a meter. And it was put out into the public there. So if you needed a reference stick, you could just literally go up to that thing, put your stick on it, and cut it to the length of a meter. And now you have a meter to take back home with you, so you can make a bed for the king when he says, I want a 3-meter long bed.
I have a bonus topic, and I've been saying it to my friends, but I want to say it officially on the podcast. I think we should get rid of time zones. I don't really see a reason for them. What are your initial thoughts on that?
Yeah, no, I think I agree. There's no reason that the sun needs to be up somewhere around 7 a.m. everywhere. Like, why, if you think about it, and it's very, I don't know if there's a word for this, but it's very equatorial of us to think about it like that way, because people in the high and low latitudes, like is it latitudes or longitudes?
Latitudes, like going up towards the North Pole.
Yeah. They don't have that luxury. They're for some of them, it's daytime at 7 a.m. and it's daytime at 7 p.m. and it's daytime at 12 p.m. So it's very it's like a equatorial thing to think that. So it seems like, there's no initial reason why that needs to be the case.
Yeah. So my argument against time zones is that there's, like you said, there's no reason other than convention for having them. I can think of I thought of 2 situations where I'm like, actually, it's nice that there are time zones, but I'll get to those. But the drawback is huge, because trying to schedule meetings, especially now that everyone's working from home and work is generally not necessarily a local thing, and you have to meet with people across the world, trying to convert time zones is so annoying. If we could all just say the meeting is happening at 4 UTC, Universal. What does UTC stand for? I'm trying to think of the time zone that like scientists use to talk about like astronomical phenomena. They're like, this happened at this time. Like, they don't talk about Pacific time. They just say 7:15 in UTC, right? Like on this day. By the Coordinated way, Universal Time.
Yeah, it's one of those French acronyms.
It's backwards. So let's just all pick one. I don't care which one. Australia could win. I don't really care. But just agree on one time that everyone uses in the world, and then we all have our meetings, and it's at 7:15, and everyone in the world knows when it's happening, rather than having to convert time zones and stuff.
Yeah, the one thing I don't know how this works out culturally, but I don't know if you know this or not, but China is all based on Beijing time. And China spans like 5 time zones.
Yes. Massive. Yeah. Outside, like if China divided up their hours as like 1/24th around the globe, it should be like 5 hours worth of time.
But and Beijing is on the East Coast, or pretty close to it. And so people on the west side of China, I don't know, they go off the same time. So for them, the sun is rising and setting at quote unquote weird times probably. But I wonder how they deal with that. I don't know if they...
At a wedding, I think it was in Kentucky or Tennessee a long time ago, and our hotel was across the time zone from where the wedding took place. And so we were trying to like figure out when to show up. Was so obnoxious. But what it made me realize is that if you're on the edge of a time zone, the sunset is like way like an hour off from what you would expect it to be. Like it's like at 4:15 in the afternoon. You're like, the sun's supposed to be setting at 5:15. Like, why is it so early? I'm like, I'm on the edge of the time zone. If I literally go across the street, it feels right. That's the right time. But trying to figure out when to leave for the wedding to get to the wedding on time was not fun.
That's a nightmare.
But exactly. If you're if you're going to go with time zones, you have to make a decision of how many. And I think the continental US having 4 is already too many, like maybe 2, if you want to make time zones a thing. But why not just get rid of them? Just go to 0 or 1 across the whole world. It doesn't really make a big difference. The one argument that I thought of for a reason time zones are good is there was something that happened in the news, and it was like a statement was released at 3:30 a.m., like wherever this happened. And that was information to me that this is important, because who is up at 3:30 in the morning writing statements to be released? And I'm like, the fact that it came out at this person's time being middle of the night, early morning means this is a big deal. Yeah. That was like additional information. So if it was just like we all just had one time zone, then that would have been lost in that like knowledge of that information.
Yeah. The other thing I can think with like meetings is like right now I work with a lot of TAs that are in China actually, and they're educating, our students from China, which is amazing. But so we set all of our meetings on Pacific Standard Time, and because we're jerks, we just let everyone else figure it out. But the thing that, so we can ask them, oh, what time is it where you are? And they'll say, oh, it's 5 a.m. And that has meaning to me.
Right.
Like, oh, it's really early in the morning. Whereas if it was one standard time, I'd ask what time it is. They'd say the same time as it is for me.
Right.
And then I don't know. So we'd have to be like, what's the sun's position in the sky? That would be like the question.
Yeah. Without time zones and like the universal understanding that 5 a.m. is not an appropriate time for a meeting for anybody. You would have to ask them like, oh, what time of day is it? And they're like early morning. And you're like, okay, that's not good. But we're just like coming up with vocab words to define the same thing as what is the local time.
Yeah.
Yeah. I could see that. But yeah, the other one was like TV used to be important, that a show got the primetime slot at 7 p.m. or something like that. And it showed in the East Coast first, and then Central Time, and then Mountain, and then Pacific. Or they would do like 7 p.m., 6 Eastern, or 6 Central. Or even they always had that 1 hour different one for like Central Time. For some reason, they didn't want to shift it for them. So yeah, if it was like the way we watched television was like, oh, the 7 o'clock time slot, everyone in the US at 7 o'clock is generally relaxing in their living room. So let's play a TV show that's popular for all the people at that time. But I don't think that's how we watch stuff anymore. Stuff isn't delayed. And we get mad when stuff isn't instantly available, like a Netflix show. Is they release it at, do they even do what time it comes out? I've never paid attention to a show that closely where it's like, oh, at midnight, this show gets released.
Yeah, I'm not sure. I don't think I've ever paid attention to it that closely either.
I do remember pre-Netflix, in particular, Breaking Bad would air on the East Coast, and then the torrents would have it up before it would air on the West Coast, so I could watch it before, like, it was actually on TV here. That was always nice.
I've done that too, yeah. Or like even now still with HBO, for instance, it'll come out with new shows on Sunday, and it comes out at 9 p.m. Eastern time, but I'm here, so I get to watch it at 6 and enjoy it. I don't have to pirate it anymore.
Yeah, just like on their network.
Yeah.
By the way, did you know how they used to do what was filmed in New York? Was it Johnny Carson?
I think so. Yeah, I think those.
Or was he LA? One of the shows that was like, whatever, any show that used to be recorded live in New York on the East Coast, and then they would show it 3 hours later on the West Coast. Do you know how they used to do that back before just like digital files and like how to air a show?
Yeah, that's an interesting question because they didn't have a digital recording of it. So did they like literally film it and super speed it like in a plane, like a Concorde over?
No, it's more wild than that. They filmed it live, had the tapes, and then 3 hours later, they would play it on a screen and put a camera up to the screen and live feed that camera to the West Coast. So the West Coast saw a video recording of a screen playing back the like recording of it.
Oh my gosh. Wow.
Yeah.
The quality of that must have been awful.
Exactly. I can't imagine. But yeah, that's how the West Coast saw like something on a 3 hour delay.
Wow. That's smarter than using the Concorde to fly across the United States. But
yeah. Yeah, just airdrop camera film rolls in LA as you fly over it. Okay, so I don't think we're getting rid of time zones completely.
I think just to add to, I think we just need to add a new vocabulary of, you're saying, if we all could understand, add a unit for the angle the sun has in the sky to our daily lives, then you'd say, okay, it's 8 a.m. UTC, 30 degrees. And you're like, oh, okay, it's 8 a.m., 50 degrees for us or whatever. Then you're like, okay, all right, you can.
But then we have the problem with the latitudes being totally off. And
true.
Like,
yeah. Maybe there's some new unit. No, yeah, I don't know.
We're just reinventing time, local time. If only there was a number to convey what's happening at the place you are.
Yeah.
How far you've progressed through the day.
I think some way you want that information, but you don't want to have to use it to schedule, basically, necessarily. Like,
oh, that's interesting. So we like everyone knows UTC, like we should all become familiar with what UTC is and then use that for scheduling. But then when we talk about local time with people, we can say, yeah, it's 11 a.m. Pacific.
Yeah, I'm not sure. I would be down to pilot a world where there is no time zones and see how it goes.
The argument but like the origins are traced back to like train scheduling. But I'm like, why didn't you just figure out one time zone? Like, why did you make time zones? Just say we are this time. And then that's everything. All flights and trains are easy to calculate how long it's going to take. You don't have to do the time zone math. Oh, I'm taking off at 6, but I'm landing at 8, but it's not 2 hours of flight. It's 3 time zones. So it's actually a 5-hour flight. So yeah.
Yeah, I see both, actually. And we've talked about it. I like both ideas. I don't know. I think we just need to learn how to combine them in a useful way.
It gets really messy. Like we were in, I think some parts of India had this. I know some countries do. They're a half hour off. Yeah. In India, it was not like an hour difference. It's like an hour and 30 minutes. We were like, I think 11 and a half hours different in time when we were in India.
Yeah, I know that through Programmers Through a Loop when they had to start programming for half-hour time zones. Mm-hmm. There's a whole video, I think, maybe by Tom Scott. I'm not 100%. That's like on how much of a hassle this is. Or Tim Scott, I think is his name.
Tom. I think it's Tom.
Is it Tom? Okay.
That was our practical overview of time. And hopefully by the next time we record, I'll finish that book and we can talk about the philosophical and physics foundational meaning of the word time.
Yeah.
Oh, our outro. So
we have to say things.
We need to get better. So yeah, check us out on Reddit at r/thehyperfine. And I'm on Instagram as the Hyperfine, but also personally as like Tortilla.
And you can find me on Twitter at Physzack, PHYZAKS. But really, I think the best way, the most interesting way to reach me, the way I'd prefer is via Reddit. So if you go onto our Reddit and put anything, I'm more likely to respond that way.
Yeah, I just figured out how to be a moderator and like get notifications when stuff happens. Because stuff would happen in there and I didn't know, even though I'm the mod. But like I thought I would just get a notification that somebody posted something, but I didn't until I just added a Chrome extension or something that did it.
Okay, you should send that to me so I can have that too.
Yeah, I forgot what it's called. Cool. All right. Yeah, I'll see you in a couple weeks.
Sounds good.
Oh, I have so many tabs open.